All right, welcome everyone to the March 25th, 2025 ASBI lunchtime webinar. If I can get my slides to advance here we go. I am Wade Bonzen with GM2 Associates. I'm the chair of the ASBI Construction Practices Work Group. And lucky for you, I'm filling in as moderator and host for today's webinar. Greg Freedy is preparing a FHWA workshop up in North Carolina and is not able to join us today, but we're going to go ahead and get started. Today's topic is construction of the William Halton cast-in-place segmental bridge. And our speaker today is Jerry Pfuntner with COE. But before we get into the presentation, just want to share with you all a few announcements. Just as a reminder, we now have a way for you to pre-register for all ASBI webinars for the entire year. You can use the QR code that's visible on your screen now. Or you can go to the surveymonkey.com web address that you see on your screen as well. You'll receive an email notice 1 month prior to each webinar, and the email will include an option to create a calendar appointment for each of those webinars. So this is a really convenient way to get these seminars on your calendar so you don't miss any throughout the entire year. Next month, the ASBI April webinar will be done in conjunction with NCBC, the National Concrete Bridge Council. If you're pre-registered for all the ASBI webinars in 2025, you will also automatically be registered for this webinar as well. And our presenter for that will be John Corvin, and he's going to present on the topic of mastering bridge geometry, insights into precast concrete segmental. So should be a really interesting presentation and probably pretty technical. The 2025 grouting certification training is coming up very quickly. It's going to be held in Austin, Texas on April 7th, which is just really less than a couple weeks away. See the ASBI website for registration, and I do want to mention to you that if you do want to go to this, the registration cutoff date is this Friday, March 28th. So if you're going to register for this, get in there and do that as soon as possible. Also want to remind everyone of the availability of the Resources for Concrete Bridge Design and Construction document recently published by AASHTO. This was the first document to be produced through the collaborative agreement between AASHTO and the National Concrete Bridge Council. And this document consists of a catalog or a virtual bookshelf of concrete bridge related resources that can be found in the U.S. bridge industry. So you can download that catalog using the QR code on your screen there, or go to the AASHTO or NCBC websites for more information. Just a few instructions for today's webinar. If you lose connection, you can rejoin the webinar in progress. Just use the same link that you used to join in the first place. You will miss content while you're away since we are live. Certificates of attendance will be issued only for those that meet the minimum time required in the session. And I can tell you from personal experience that you want to keep the GoToWebinar window as the active window on your screen. That's how GoToWebinar counts the amount of time that you are attending or active in the webinar. So try to keep that window active on your screen the entire time. We'll email out attendance certificates for your attendance in about a week, so keep an eye on that email. And then of course we'll do a Q&A session at the end of this presentation. For questions, using your desktop app, you can submit your questions at any time during the session. No need to wait till the end. We will do the Q&A at the end of the session. So look for the little questions menu with a little drop-down arrow, and then you can type your questions directly into the question box as shown on the screen here. For those of you that are on a mobile device like an iPhone or an iPad or similar, there's a little question mark icon in the upper right-hand corner. So you can click on that, and then that'll take you to a little dialog box to type in your question. All right, today's speaker is Jerry Pfuntner of COE. He is a technical director with COE North America. Jerry has a uniquely diverse and comprehensive background in bridge engineering, with extensive experience spanning design, construction engineering, field engineering, bridge inspection, and consulting. He's played a pivotal role in the design of various bridge types, including flat slab, pre-stressed I-girder, steel girder, precast segmental balanced cantilever, cast-in-place segmental, precast span-by-span, tied arch, and cable-stayed bridges. His notable expertise encompasses ship impact analysis, finite element analysis, seismic analysis, strut and time modeling, and time-dependent analysis. Jerry holds a Bachelor of Science in Civil Engineering and a Master of Engineering from the University of Florida, where he also contributes as a bridge engineering instructor. So I'm going to hand it over to Jerry now to be the presenter. And Jerry, go ahead and share your screen.
Okay, thanks, Wade. Can you see my screen?
Yep, looks good. Thank you.
All right, perfect. Okay, this afternoon we're going to talk about the construction of the William Halton cast-in-place segmental bridge. As you can see from the photo there, this is not your average cast-in-place segmental with the temporary works that we have here. We'll discuss that over the presentation. So a little bit about the project. It's located in Oakville, Ontario, Canada, near Toronto, which is a suburb of that. It's part of the William Halton Parkway Extension Project. That's going to be completed in late 2025 this year. There are two new bridges over the 16-mile creek that you see there below and to the left. It's got 2 lanes of traffic and pedestrian walkways, and it's going to help ease traffic in that rapidly growing area there in Oakville, which is very nice. The owner is the Halton region. The engineer of record for this structure is WSP Canada. The contractor that we've been working with are great is Bott Construction, and COE is the construction engineer on this project. So a little bit about the bridge that you saw in the photo on the last slide. It's a 3-span segmental bridge. One thing you'll quickly notice that the first span, 95 meters, is very close to the center span, 120 meters and 65. So that's part of the challenge of this project. We're quite a ways off the floor from the creek, about 150 feet, 38 meters. Our box varies in height from 3 to 6 meters. It's 14 meters wide, and it's going to be covered with 90 millimeters of asphalt and a waterproofing layer. Here you can see COE's role. So we did straight construction analysis, erection and casting manuals, temporary works, geometry control, shop drawings, and construction support. You can see me over there on the right. One thing that's interesting in Canada is that as the practicing professional or responsible professional, you're going to be on site. It's kind of a requirement, especially from the PE board there. They want to see documentation that you go out there and actually physically see the work as it's progressing through. So you'll get to see your job many times like I did out there. Next, we'll spend a couple slides here talking about the construction methodology. So most of it was pretty standard cast in place, segmental balance cantilever. We have 2 pairs or 4 travelers, 2 pairs on each cantilever. And then we did have an extended cantilever on the west pier, which we'll be talking about extensively here. And shoring towers were used for the end span construction as is typical. And then we added some closure segments from the base design to be able to assist us with closing up and making our geometry adjustments just right at the end of each cantilever. So our sequence, pretty typical. Pier tables were constructed first, and then we progressed on to the cantilever segments. On each cantilever, we closed up the midspan of the main span first, and then closed on to the backspan, and then we had the extended cantilever that you see here in the orange, and then closed up with a closure segment onto the pier segment, the expansion segment there at the west abutment. This photograph just kind of highlights those different aspects of it. You can see, access was not bad down below from being able to put cranes within an area. This pier ideally would have been located right where this creek is in order to have a little bit better span distribution, but due to environmental restrictions, it's not. So that's why we're talking about that extended cantilever that was required to get over here to the west abutment for the project. Substructure was fairly typical. One thing we liked was seeing the twin, pier columns that helps out with strength, but also with geometry control. So it gives us a very stable pier table system to be able to erect without a lot of whole movement of the substructure during cantilever erection. So keeping it very stable as we progressed outward. You can see they were integral piers at the top end of the pier table and a pretty extensive formwork system for the pier table construction itself. That leads into the pier tables. You can see they're nice and long for providing a platform for our form travelers on there, and then extensive diaphragms as you typically would see, and to match up to the twin pier columns that we had within the for the substructure supporting them. Typical segments, our cycle was a little bit different than you would normally see. Typically you have a tendon that's a cantilever tendon for each segment. So you would have from the pier table, you would have the ability to stress a tendon from the end of the pier table to the first segment, and then you could launch the traveler. Whereas in this configuration, the post tensioning was one cantilever tendon for each pair of segments. And so, which is of course, doable, but it is a little bit slower with the cycle for erection to be able to have to wait for both segments to be cast and then stress our tendons before moving forward. Our typical cycle, so we had launch forward, set up the formwork as you would normally do, early morning geometry control, and then setting up, placing the rebar, post tensioning, all those good things that we have in our typical segments, and then casting the concrete once that's completed, and then as you can see there, screeding those to the proper elevation through the segment. The extended cantilever is where this project starts to get interesting. So in order to have your typical balanced cantilever construction that we have with cantilever tendons all the way through to the end, to the midspan pour, in order to extend the cantilever, so the designer chose not to have cantilever post tensioning integrated into the segment. So beyond the typical balanced cantilever segments, we have no cantilever post tensioning in here. So all of the support of those additional segments is provided by this temporary stay system. So it really acts as external post tension, or it's almost like an temporary extra dose bridge is the way I would describe this, in the way that they actually performed and behaved. And so by anchoring back and extending the tendons way above the level of the deck, we got the benefit of the added eccentricity and the support to be able to go way beyond a few segments to the typical range that we would have for the balanced cantilever segments, and then anchoring them back into that completed backspan for the stay cable anchorage. So this cycle was a little bit different. We were doing unidirectional form fabric construction. Once we got beyond there, as I mentioned earlier, we closed the backspan and also the main span cantilever, and so that allowed us to complete once the construction of the temporary tower and begin anchoring the stays into the backspan, the main span. and then anchoring them forward right behind the form traveler as we progressed out onto that extended cantilever. The anchorages, the boxes themselves, are at the beginning of each newly cast segment, so we end up also adding some external PT bars and above the deck level, mainly for shear lag effects for that segment. The anchor box was close to the edge so that we would provide some pre-compression close to where that anchorage zone was with this additional external post-tensioning. Next, I'll talk a few minutes about the construction analysis. So we utilized Sophistic for this job to model the structure in 3D. So we utilized Grasshopper, which you can see on the left hand, the script that was provides a graphical solution to be able to put all the inputs for the model. So the model that you see, the Sophistic model, and this is a Rhino visualization model, are all generated from the inputs that are here within Grasshopper. So this eliminates the individual keystrokes that are required for a code input and gives us a graphical solution to be able to bring in variables and inputs within this and allow us to auto-generate our model, which is highly efficient from a design, and also it makes it easier to check once we have the model created to be able to check our inputs for all the different variables that we have within there. Here you can see a good view of the varied post-tensioning systems that we have within this particular structure. So we have the typical cantilever tendons, we have our continuity tendons in the positive moment regions, and then distinctly you'll see that the cantilever tendons end right there at the end of the balanced cantilever unit, and that there are no cantilever tendons beyond this. We're strictly relying on the temporary extra dose cables to be able to provide that support and of those forces for the extended cantilever throughout that construction. In Canada, we have the CSA 6 is the predominant code that's required, so it doesn't directly address most of concrete segmental construction. So it's a blend of combinations from the Canadian CSA 6 code and also ASHTO, which they reference into their specifications for this project. So we used a combination of the ASHTO construction combinations and also the Canadian ones, and incorporated the design values and different loadings from ASHTO for like construction equipment, wind uplift, differential, and things of that nature, where the Canadian code was silent. So we had to do a few extra checks to be able to make sure we satisfied both requirements on this particular project. Our construction staging was set up to meet the requirements for geometry control and all the critical activities during cantilever construction. All phases were modeled to capture worst case effects for the load combinations, as well as targeting our geometry control stages. Here you can see to the right an example of the Sophistic output where we had the individual stages that were critical for geometry control, and then we have the ability to handle our moving permanent loads like the movable form traveler system, and analyzing creep and shrinkage effects all throughout construction through the time periods that we were building them, and also accommodating the temporary fixities and potential locked-in forces that are generated from segmental bridge construction, removal of travelers, the stay cable system. All those were able to be incorporated within our construction staged analysis, which was a little bit unique for this project with the temporary extra dose stay condition that we had. Looking at some of the longitudinal stress plots, so you can see on the right the Sophistic output that generates all this. The numbers look a little off because they're all in metric, so those are in MPa, and we did look at all the stress points at the center line, as well as the left and right hand, bottom and top, and follow the construction stress requirements from the Canadian code. A little bit different than ASHTO, but in general, the design is not much different than what we would have here in the United States as well. We did make a few modifications. So some of the equipment, the Traveler was a little heavier than what was assumed in the design. So there was some modifications for additional, shear capacity required, near the piers. We increased the top slab longitudinal rebar in the negative moment region. And then we did increase the top slab, beyond where the stay cables were. A lot of that due to the fact that we, as construction engineers working up in Canada, considered that with the weather conditions up there, we were not going to have bonded post tensioning at all times. And so we made sure that we had the proper amount of reinforcement, additional reinforcement, to make up for the fact that we couldn't count on additional stress gain in the cantilever tendons, because they were acting almost like external tendons. We also had the increase in loads during construction, and then those shear lag effects I was mentioning earlier. So, the distribution of tendons in that region with the extended cantilever, we made sure that we would have, where we have tension, a well-distributed amount of rebar through those zones as well, to make sure we had very small cracking, if any. The temporary stays, so we use nonlinear, like a stay cable analysis that we can do within Sophistic. And so we generated our cable axial forces as part of the design in order to balance that extended cantilever. And then, so we were also looking at the negative moment region, the top slab stresses due to this negative bending, but actually the stay cables in certain stages would create some tensile zones in the bottom as well. So we were managing that back and forth with determining the axial force that was required for the temporary cables. In the end, they were performing much like post-tensioning tendons. We were able to stress them to force. They held their force, largely because of the box girder section has a pretty stiff moment of inertia and stiffness associated with it. So we didn't have the same concerns that you would have with a cable stay bridge, where we have much more flexible structure. This one behaved very well as a bending element, and then we were consistently able to generate these. We did end up stressing these up to 70%. We were comfortable with that, given that the deflections that we had during cantilever construction were small, and there weren't very much of a change in the work points between where the cables were during all phases of construction. So we had a very minimal stress change all throughout the construction process. Camber is where you can begin to see some pretty good differences between the traditional balanced cantilever and then getting into the extended cantilever. So you can see where we were in regions where we were doing true balanced cantilever construction. The cambers were fairly consistent, what you would normally see for a bridge of this size and magnitude. But when we get out to the extended cantilever, that's where you can really see some increase in the bending. And you notice that's this region with the extended cantilever is a constant depth box girder, and so these deformations got to be pretty significant within the camber themselves, even with the temporary external extras cables working within them. So we were dealing with some bigger numbers than we're typically seeing. And so we'll discuss a little bit later the geometry and some of the issues that we had with keeping that all together on this project. Quickly, our transverse construction analysis. So we had local checks. We had many cranes on the deck, the form traveler itself, concentrated forces from our cable anchorages, the post-tensioning, and then looking at the different items that we had within the deck. A lot of that had to do with the cranes. Also, we had a spider boom crane to help place with concrete placement out there. And so analyzing the local effects as you would typically do for a concrete segmental bridge, to analyze those during construction to make sure we were within and following the project requirements for allowable stress conditions. Next, we'll start digging into some of the temporary works. So the temporary stake tower really is what made this work to be able to have this extended cantilever. So as I noted earlier, the balanced cantilever part ends right about here. And so we're in a constant depth region that extended the cantilever all the way out to get to this west abutment. And that was because we couldn't get in this creek that's back over here. And so you can see that the temporary tower itself is extensive in order to get that number of segments. It's quite a structure itself. It's almost a shame to have to take it down, but it was necessary to help us get that. It applies external axial forces that for these regions that don't have cantilever post-tensioning tendons, and so it's acting to provide an axial force as well as the bending moment required to be able to resist for these segments to have that positive or negative bending component to be able to resist that. We did have a fixed connection of the temporary tower at the pier table itself. So we did not have it where it was truly pinned. We wanted to have the rigidity there. And then the stays actually greatly affected the geometry control under thermal loadings. And so we'll talk about that here in a second as well. The temporary tower, we actually, utilized 3D modeling to be able to generate this and the details and integrating this into the shop drawings, as well as producing all of the fabrication drawings for the tower or directly off this 3D model is quite handy. It also helped to create the installation manual that you see here. This is the actual graphics to use to be able to describe how we're going to install this. One of the things in the temporary tower is the first cables that were constructed. You can see we have a cable anchor box instead of saddles that we used for the remaining ones. This greatly helped us to be able to stabilize the tower for the stressing of all the remaining ones. So I chose to have fixed anchorages on both sides, so that way we could stress a couple of strands at this bottom level, and then that greatly stabilized the tower itself and allowed us to have just simple saddles for all of the rest of them. And this eliminated Bob from having to get up there and deal with additional anchorages and installation procedures. So we were actually going to be able to drape these right over the saddles, and it worked very well with that bottom stay cable acting as an anchor almost, as well as the stay system, and providing stability to the tower itself. So you can see there's a good view looking down the deck. You get a good feel for the stay cables themselves and how extensive the tower is. The height was chosen to, minimize our efficiency. We're able to keep these tendons down to 19 strands each one, and then with the heights of balancing the height of this and the amount of complexity that we have within there. So that gives you a good look down there, and you can also see a good view here of the anchor boxes that we actually had to do. So if you ever wonder what you have to do to mount a tendon, a 19-strand tendon eccentric to a deck at that level, that's what it takes. It's quite a piece of steel to be able to do that and transfer that safely to the box girder section and get those loads into it at that level. And we'll describe why we had to do it at that height here in just a second. The tower itself, as I mentioned, is fixed. We wanted that rigidity within the box, and we have a nice pier table to be able to secure it to. So it's just on standard grout pads, and then we fastened it with tie downs from Whalers beams down there directly, and so that was a fairly efficient part of that system. And then just a few details from the tower itself. So here is the cable box that we utilized for the first or lower, stay cable. And the rest of them, you can see the saddles. So there's a good view of the cable box system. All the hardware was standard, post-tensioning. So we didn't have any stay cable details, even though we call them stays. They're just post-tensioning systems that were utilized within these boxes and the anchor system to be able to utilize that. So it's fairly economical, strand and anchorage systems from that point of view. And so the first one was the anchor box, which was very stable. And then we utilized these saddle details. So we just took pipe sections, cut them in half, and then put a gusset, cut plate on top of it, and then we're able to run and drape the strand directly in within this saddle in that confinement zone, and then run those directly over the top, so that all stressing was to be able to beyond the first one was to be accomplished from the level of the deck itself. As far as the cable anchor boxes, you've seen it's pretty large size, and so there were some different concepts. So the contract plan design was to, a blister internal to the segment, right inside the web wall location. And then other ideas we came up with was an external anchorage concept. We can actually get the stays outside of the box itself and have an external beam. One of the big things when you look at these types of details, running back of the napkin kind of stuff, is that, look at the devil's in the details. So part of what this requires is a block out. And then when actually you take the stay cables at that inclination, the size of the block out is huge. So it's almost an entire segment length, what it would be. And then you couple that with the detail being right there in that socket of the web, right where the form traveler would bear down. So you quickly run out of room for this detail. It was almost the same thing with this type of a detail. When you state, you have this concept here, and you look at the same type of inclination, the amount of box that you have to block out in order to do this, it gets to be pretty extensive. Additionally, if you look at this transfer beam, it looks nice on this detail, but when you actually start putting some numbers to what this would be to be able to transfer that load into the box girder in the bottom slab, it gets pretty big pretty quick. And so so we went through a few ideas, and in the end, Bot Construction wanted to have something that they could utilize from the deck level, keep themselves at the deck to be able to install, remove, replace, move around. And so this cable box system was actually developed to be able to transfer the load of the stay cables within this region here, and then get them down into the level of the box girder here. So we actually designed this. You have an eccentricity to the segment. There's a tie down that's down and within this region here. We have the bearing location here to form our couple to be able to resist that. So the steel that you see here is all about the transfer mechanism to get this anchorage force at an eccentricity to this the couple that can be formed by the tie down and the compression zone. Probably the biggest other issue that you have is this all has to be done inside of the form traveler, the rails that we have in there. So it's also got to go between the rails and has to be stressed between them as well. So that created an extra deal, and that's why some of the height that you see here is actually because of that fact that we have to install and stress them in between the form traveler rails on the leading edge. And so some of the biggest parts of it we'll show you here in a second. We have a lug that's down below here that assists us with transferring this 19 strand load directly into the segment itself at a lower level. And then also, a lot of clashes that had to be resolved as well. And this is where our 3D modeling really came into play. So we created a full 3D model of this as well to be able to not only make sure that we could fit within the traveler, we developed 3D models of that as well to to integrate the two of them together. And then the parts of the cast and lug and the tie down all went into the shop drawings, and then this went to the fabricator to be able to fabricate these things. And then the checks that we made to also take the post tensioning ram and put them on the end of this head to be able to make sure that we would fit between this gap. There was a lot of checking for clearances that happened well before we ever built anything. And so our happy day was when we were able to stress this thing and actually everything fit between the traveler and all that. So I would say, 15, 20 years ago, when we didn't have all this 3D technology at this level to be able to do that, this would have been a real nail biter to have this. But today we're able to utilize these advances in CAD technology and 3D modeling to be able to have this. And then all the drawings that you see here, those are all created from the 3D model. So we utilize this extensively to be able to develop our temporary work systems and drawings. And as you can see here, section views, cuts, all that are all very easily performed and integrated to provide to fabricators. So there's a lot of equipment up top that you see to be able to have that, but actually inside the box it's not that bad, which I think is a kind of a tribute to that part of the design. So we have this cast-in lug that we developed to be able to have the tie down within here, and then all of the shear key that was developed actually transports that load into a bearing plate that you see here, and then we integrated reinforcing to be able to create almost like a spiral to be able to a confinement zone well ahead of that in order to get those forces from that anchorage above the level of the deck into the box with this level of detail that we have within here. So not much into the box, but a whole lot out to make that eccentricity work within it. But here you can see the extended cantilever. Each segment gets its own, stay, and then again, that's replacing the impact of cantilever post-tensioning tendons out there. And then here's a good view where you can see the anchor box is actually right in between those traveler rails. And then here is a view of them, off the equipment, but this is where they're stressing in between the traveler rails themselves. And so a lot of coordination between the form traveler supplier and us to make sure we were able to be comfortable with being able to put that in there. And then again, the height of this was actually selected to allow for the stressing not only to occur above the level of the deck, but also we had to do it right there in the middle of the traveler as well. So that's, if we, I would suggest if something like this had to be done in the future, a little bit of post-tensioning that would allow us to advance this beyond and then stress behind would be a benefit to be able to reduce the size and magnitude of this particular detail for the project. Complex bridge engineering typically involves some tough work, and these guys right here are doing some tough work to be able to install this in between the travelers in tight quarters. Again, this is where the 3D modeling really assisted us with being able to make sure that we could get the tools and equipment to be able to tie this thing down inside reasonably within those traveler rails and actually install all this stuff. And so this was quite, an activity that had to be done to make sure we were all comfortable with it. And but in the end, it worked out. Like I say, they're heavy, and what they had to do to install these was significant, but it all fit up, and it worked within the project to serve the purpose and the need that we had for this to make this happen on the top side of the deck. Here you can see we stressed with a monostrand jack. Took advantage of the extra dose bridge concept, and that the girders themselves had a good stiffness, and so we were able to stress these strand by strand and to force again, and then ended up plus or minus 5% was not a problem. They stressed out very well, and they were actually able to install even the longest cables in about an hour and a half or so. So it wasn't really that demanding once they got everything in place and all that. So this particular part of it held very well, and then the stay cables themselves did not have a lot of fluctuation in force throughout the construction sequencing. Next, I'll talk a little bit about geometry control. So typically for a cast in place segmental balanced cantilever, you're going to have your first critical stage is really the setup, where you are advancing the form traveler forward, and then you're setting up, and after that early morning survey to be able to set the bulkhead to where we're set up for the next segment itself. And then after casting is when we do our after cast survey, and we see what geometry was actually achieved. We're looking to make sure that the angle break relationship between this new segment and the cantilever is in the proper alignment. And then, we make corrections as we go through. Bob did a very good job of, casting all through this process. And so we had good geometry to work with. But we did have the added nuance of the extended cantilever and adding external temporary stays as part of that activity of our sequencing. So we developed this geometry control program, which is, spreadsheet based, to be able to have all of the different construction stages, cable installation, and then our setups after casts. All these that we talked about earlier in the stage construction analysis were all incorporated within the software to be able to have the displacements at any given phase and stage of construction, that we would get theoretical elevations that we would be able to survey and then compare where we're at versus what we had anticipated theoretically from the project site. Now, the added complication of the stake cables, it was very easy to do all this when we were in typical balanced cantilever erection. But when we got to actually surveying and setting up segments with stake cables, that got to be where it was much more interesting to have to add that whole activity, and then the change of the stake cable stressing was much different than you would have for a cantilever tendon. We actually moved the bridge, and the external cables themselves would actually heat up during the day, and so a lot of the displacement that we would get from thermal effects, about probably 2/3 of the movement on a given daily cycle was from the actual segment itself heating up and then curling down like we would normally see. But then we also had to add in the heating up of the stake cables themselves, and then that also had probably about 25 to 30% of the delta that we would see. So we went through an extensive program of monitoring this during construction to be able to early establish the behavior of the bridge relative to our theoretical values. That's important on any job. I always say that the best information you have to set up your next segment is the previous segment. And so if you take the behavior of that and compare it to what you have theoretical, I believe the bridge more than I believe the software program most of the time. And especially when you add the stake cables within there, you have a little bit of a nuance with the construction and looking at the theoretical numbers versus actual. I always say that geometry control is 25% art, 75% science. Part of it is looking at the bridge and then understanding that we don't have everything within these numbers in our models, and then understanding our environmental conditions, what loadings we have to be able to evaluate and make decisions to get the proper geometry is critical as well. So we learned a lot as far as the geometry control. Thermal effects got to be quite a thing for the extended cantilevers. As we began getting out to the extended cantilever portion, we started monitoring temperature, not only at first light, but we started taking afternoon surveys. So we would gain all that information. We wanted to know exactly how much the bridge was moving during the day and tracking thermal displacements versus ambient temperature, so that we would kind of have an estimate of where we would be when we got to the end of that extended cantilever relative to where we first were starting, so that we can incorporate it into all those great theoretical numbers that we had, but we can make our judgments on thermal corrections that need to be incorporated as well. An interesting thing that you would have in Canada, at the time, spring lasts about 3 weeks up there, and then summer lasts about 3 weeks. And but we had the time that we actually closed, which you guessed it, was right in the middle of this transition between spring to summer. And all throughout the late winter months, they promised me that this bridge would never see more than 25, 27 degrees Celsius. But we ended up having one of the hottest summers out there, and we had some pretty significant swings. You can see there, we did W32, we were 22 degrees C, which is about a nice comfortable 75 degrees to us. And then by the time we got 2 segments later, we were in the 90s in Canada. So significantly warmer, a big change within that. And so we brought some pretty significant swings in the values for our geometry when we're actually evaluating the cantilever and the stays that affect itself, to be able to monitor this. And this is really where we didn't realize at the time, but when we were doing those early surveys for first light and then tracking afternoons versus ambient. So we had a pretty good balance of what the behavior would be versus putting ourselves in catch-up mode, realizing that we had some pretty wild swings. And so we were able to use that early information to be able to make judgments as we were casting, 32, 33, 34, 35, and coming on into closure to be able to bring this thing home without having to. We didn't have to do a single stay, correction or adjustment, and we had, minor corrections as we even came in to the final closure. We were actually able to close with just a minor geometry adjustment using just the traveler, post off the traveler itself. We didn't have to strong back or do any additional jacking of the bridge up or anything like that. So all that effort that we had put into to understanding it, paid off very well to be able to close on that final segment and have very good geometry. As you can see here, it's a good looking bridge with that extended cantilever system itself. A quick look at our closures. So I guess mentioned with good geometry control and the monitoring that we had, we were able to close with very minimal counterweighting or adjustments that we had within these processes. And so the closures themselves worked out very well to be able to incorporate the deck and then close on the cantilever and all of these that we would actually use the foam traveler itself. So we would launch forward and then grip onto the adjacent cantilever, make our minor corrections. All closures we're able to do with a simple post detail that we had on the front of the traveler to be able to make those adjustments and then incorporate those into the final casting to have a very good geometry system we have within there. Our current project status, this is where we're at. So last year we finished up the bridge that you can see on the far end. That's the one I've been showing you all the pictures of. This is a recent photograph. So Bot has actually been doing very well in casting in the wintertime. So most of the segments that you see out there are wintertime casts. So they're looking forward to coming into spring and then finishing up these cantilevers and doing the same process that we did for this left-hand side bridge that we did on that right-hand bridge up on the upper side over there. Couple of quick lessons learned. So the extended cantilever was, quite the detail. That actually what made this probably the most complicated CIP segmental I've ever done. The external temporary post-tensioning system is definitely a feasible method for extending the cantilever length, as we had to do to get over that creek and keep the pier outside of its within it. But I will say, it's an expensive alternative. Having the additional details that you saw with the anchor boxes and the time it took, extra measures to, it was slow progress for many of the segments, especially the couple of early ones. They were able to achieve, about a week and a half or so, per segment there at the end, but that was slow go at the beginning. And the other big one is that developing a geometry control plan that incorporate those thermal displacements to take what we've traditionally done, the methods and means that we've had, with our spreadsheet geometry. We've done, balanced cantilevers many times like this, but incorporating the stay system. We kind of drew from our cable stay geometry experience and combine that with what we would utilize for our cast in place balanced cantilever and kind of blended the two together. But I can't emphasize enough the ability to incorporate that early, morning surveys, afternoon, understanding the behavior of the bridge and how the temporary stays affected us, paid off to be able to understand our bridge. So that we got there to the last 2 or 3 segments, we were able to, work with that wild temperature swings that we had and then develop a good plan to be able to close this up without having to do very much at all to be able to get to final closure and then have a good geometry structure. So with that, I will take any questions that we have.
All right, thank you, Jerry. That's a really interesting project. Lots of questions. So First of all, just to set the stage a little bit here, and maybe you said at the beginning, was this a design bid build type procurement?
It was design bid build, yes.
Okay, great, good. So some questions related to that. When you were looking at it from a construction engineering point of view, did you look at perhaps reworking the longitudinal tenon layout to try to eliminate or minimize the amount of temporary stays and things that you had to have?
That was something that we discussed with BOT. One of the things that we had was the constraints, I'll say, is that, the timing of it. So there is a delivery time that's associated with this. And so many of the things that, we could have done as a construction engineer to look at, extra PT, but that would have taken time. We would have had to, with the contractual relationship, have the EOR responsibility come to us and to BOT Construction. This was actually their first segmental bridge that they've ever done, and so that's something they were not really interested in entertaining. And so we pretty much followed the bid design as it was, and actually it was, it was constructible and achievable, certainly. And but there were some things that we could have done, working with a contractor to be able to have, once we're sitting there across the table to do that. Yes.
Yeah, that's an interesting answer, because it sort of highlights the fact that sometimes there's not a technical reason you're doing something, but sometimes there are other constraints or considerations that are non-technical. So similarly, did you look at the idea, or was it possible to perhaps put a prop in underneath that long cantilever to, again, help kind of minimize the amount of temporary stays you might need?
Actually, there's a couple things. So number one, there's environmental restrictions of the floor. So the access that you saw in between the two piers was pretty much what you had. And then those hillsides that you see are pretty steep. And so creating a platform to be able to do that for a prop would be something. And then, but that also would have required still the addition of the negative moment region post tensioning over the top of that, and also a design change, because we would have had a support not within there. So we would have again had to be EOR. So that was a consideration, I'll say, but we had actually looked at maybe even extending the length of the end span units out a bit, and maybe even cantilevering off of those as a way. But again, those were thrown out because of the time, number one, and then the responsibility for the structure itself.
Okay, how many total segments were there for the project?
I've got it in my, sorry, I'm having to flip through here. I think there was like 58 per side. Apologize to everybody for flipping through.
No problem.
Yeah, 58 cast in place segments, 2 end span sections, a couple of pier tables, and your 3 closures.
Okay.
So not a huge.
That, yeah, so that kind of project probably would not justify attempting to do the job precast, especially with the idea of not wanting to be the engineer of record. So
yeah, and then also that goes along with that, erecting in the back spans without being able, especially as you see here in this 5 meter span, you have virtually no access through the entire part. So to bring in a precast segment and and install this region right here would be almost impossible.
And do you have a sense of what the typical cantilever cycle took in terms of number of working days, especially with the extra time needed for the stay cable work?
Well, because of the cantilever tendon going all the way across between the 2 segments, the cycle is more in the 2-week range.
And what was the reason for that particular tendon layout? That's a little bit unusual for cast in place segmental.
It is, and it's that was the designer's choice.
Okay. Okay. Was there a consideration of using lightweight concrete to reduce the added load on the end of the extended cantilever? The submitter noted that that's been done on some bridges in Norway where the span configuration was not ideal.
Yeah, if you look at, I think this job, I mean, lightweight concrete could be something that could be utilized, but what the big number is the number right here, 8 segments in this extended cantilever. And then we looked at some, like you mentioned, you asked earlier about alternative, means. That's a lot to add on to that. And so once you make the decision to go to a temporary stay, and you're basically going to procure and install all of that, I think you're pretty much locked into that. And so to add the time required to look at lightweight concrete, especially with the durability concerns up there in Canada with the environment that they have, I don't know that would have flown on this project.
Do you have a total cost for the project and an estimated cost per unit deck area, square feet or square meters?
I actually don't have that information in front of me.
All right. And did you all do any type of project-specific wind studies to take a look at the temporary towers and the stays during construction? Was that a consideration?
The only thing we didn't, we did, apply the wind values that we had off the contract drawings that were available, and then we did some simple screw number checks on the stays themselves with this length and the stressing force to make sure we didn't really think there were going to be any vibration issues. But I will say that when you're standing out there on the deck and you get a 15-mile-an-hour wind, you can see the stay cables vibrate. It's quite with the bare strands. It definitely happens, but nothing significant really, amplitude-wise.
Were there any seismic design considerations for the project?
That I have to look up what the EOR had in the design criteria. So as construction engineering, we did not have to incorporate that for this project.
Yeah, given the short window of time that the bridge is under construction. Yeah. Does the bridge carry any utilities like gas, power, water, telephone?
I think the only real one is the internal drainage system that it has. It's got there's no dropping of the water within there, so it only has its own internal. I will say, if you look at the pipes required in Canada to be able to prevent them from icing over inside of the pipes, you wouldn't believe how big the insulation is. So the 12-inch diameter pipe is actually about 2.5 feet in diameter, and they're heavy to include the insulation that's required. That's something you wouldn't think about sitting here in Florida or here in Southern United States. It was a significant thing.
Yeah, that's interesting. You're using the same temporary stay system for both bridges, correct?
That's right. So the details that you saw there mostly are reusable. So they'll be able to take those and they're reusing them now on the second bridge. So that there is some savings there from being able to just take that by crane and just plunk it right across to the other structure.
You mentioned that you took a look at the idea of having all or some of the cantilever tendons analyzed as unbonded due to the potential for not being able to grout those during cold weather. Was that something that was included in the design, or was that something that you all did as the construction engineer?
That's something that we did. Yeah.
And did you assume that all of the tendons were unbonded? Just conservatively, or was there a sort of a balance that you used?
We do. We actually did. We were able to look at that, recognizing that the amount of time, we've worked up in Canada before many times, and so there's a significant period where you just are above that, the threshold of when you can grout. And so that's where a little bit of extra deck reinforcing to be able to make up that delta, what we would need want to have for the capacity, is definitely worth it, to be able to not have to call your contractor and say you have to stop at certain points. And so we typically will do for like a gantry, where we have a gantry on there, you need to have some unbonded in there or some bonded tendons, so that we have that. But we were comfortable with just the one traveler out there to be able to have the additional mile take its place relative to the capacity.
I think I saw from your 3D model that out on that extended cantilever, there were bottom slab continuity tendons that anchored pretty much back to the abutment segment, but then there was, you know, obviously the top slab cantilever tendons stopped fairly short of the end of the cantilever. So there was part of the cycle there where you're launching the form traveler out to cast the next segment. And so the little mini cantilever that's formed there is basically just mildly reinforced in the top slab. Is that correct?
Well, and that's where we had the temporary external tendons on the deck, those PT bars. And so we incorporated those within the design to be able to kind of make up where we were, you know, launching forward, to have some pre-compression across those. So we didn't want to have any joints opening as we were, you know, setting up the traveler moving forward. And so those bars are there actually to help augment the additional mile reinforcing and make sure that we had a good serviceable joint and didn't have any openings.
And what was the final allowable tensile stress in the longitudinal tensile stress in the superstructure, like in the service condition?
So in Canada, I'll get to that slide here. So in megapascal, you can see that Canada works a little bit, they have a little bit different criteria from just a pure allowable stress. And so a lot of it depends on whether you crack or you uncrack concrete. And so like you can see here during construction, we have uncracked concrete. You can go to 1.4 MPa, which is about 200 PSI. So it's a little different we have within there. So and then depending upon you know, where you're at with the project, you can have similar to our 3 square root, but you have to provide mild reinforcing to be able to make up the difference, and a little bit more of extensive weight than we have within our US code. So it's close to what we have, but it's not exactly, you know, the requirements for a rebar when you go into tension is a little bit different than with the CSA 6. And then compression allowables are very similar to what we have in the United States as well.
Okay, great. Sorry, I'm just trying to eliminate duplicates in the questions here.
Had a lot of them.
Yeah. Yeah, lots of questions. You talked about tracking the movements due to temperature.
Mm-hmm.
And that can be very complex because not only is it ambient temperature, but it's also the thermal gradient through the depth of the box. So as the, you know, the top slab heats up, the bottom portion of the box is, you know, cooler for a while, and that's ever changing and very dynamic. Did you see good correlation with your cantilever deflections versus ambient, or were you all measuring the thermal gradient as well?
Yeah, so thermal gradient, we didn't have, you know, thermocouples installed, you know, top and bottom, and what we've typically done in the past is we try and have it versus ambient, and we consider that, you know, you're on most days you're going to have sunshine, heating up the deck, lowering it down, and so we relate that back to ambient. We've been successful to be able to do that as far as understanding the behavior of the actual girder itself. And so that behavior was pretty consistent relative to ambient, so on a daily swing. Now what varied was the cables themselves, and so obviously they heat up faster than the concrete does, and they also cool down faster than the concrete does. And so that's where we saw that 25 to 30% variation. That was the stake cables part of it, happening a little bit faster. And so you had to monitor that that component of the overall deflection a little closer.
Sounds pretty complicated.
It was.
Back to the unbonded tendons real quick. Couple questions there. Did you all, when you were looking at the unbonded tendons and doing the design accounting for that, did you look at the ultimate capacity with unbonded tendons as well, or just service or just construction stresses?
Yeah, so, well, we have service construction stresses, obviously, to make sure we have, we fall within the project requirements, but then we also do our ultimate checks as well, and that is considering them unbonded. So, especially with unbonded cantilever tendons, they don't really have the ability to, increase or elongate unless really bad things happen. So that's pretty much at your FSE, your effective stress. And that's where the additional mild reinforcing comes in to make up any delta that we need to have between the ultimate demand and the capacity.
And there's a question here about how you model the bonded versus unbonded tendons in Sophistic.
Well, Sophistic has, the software has the, you can tell when you grout a tendon or not. We do all of our calculations external to, when we're looking at capacity, external to the software itself. So we don't let the software tell us whether we're good or not. We have our own independent sheets that we developed to be able to use strain compatibility and other methods to be able to evaluate our capacities.
Okay. Was there a need to camber the columns on the project?
We did not.
Okay.
There was not, no.
And how did the cold weather concreting and construction considerations go for the project? It looks like they basically worked straight through the winter. Is that correct?
They did, and Bott is a local contractor up there, and so they're well aware of working in that type of environment. Obviously, in Canada, the requirements for cold weather concreting are pretty significant, and but they had to work within that. So that you're definitely looking at a slower cycle in the wintertime versus summertime.
Yeah. Do they use the the form travelers as sort of framework to build some enclosures and things to be able to heat their segments?
Yeah, that's what you saw, some of the orange, the wrapping around there. So they, do like what you typically see, the wrap segment to be able to heat in that area locally at the end of the cantilever.
All right, great. Well, I think we are at the point where we need to probably call it for time today, but really appreciate the very heavily engaged question asking in the session today. I tried to hit as many questions as I could that eliminate some of the duplicates, but great presentation, Jerry. Really appreciate it. And I want to thank everybody for attending today.
Thanks, everybody.
All right, everybody have a good day.